Hi everyone, so this is your first lesson of Unit 2. It's lesson 2.1, and we're going to cover exponents today. Okay, so starting right from the basics before we talk about some different operations you can do with them. So an exponent is basically an easier way to write when you have the same number multiplied together multiple times. So when we look at an example, let's look at the number 5. Okay, so if you have 5 times 5 times 5 times 5, 4 times. If you do this as an exponent, you can write that as 5 to the exponent 4, which means 5 multiplied by itself, a total of 4 times. Okay, and when you see it written as an exponent, this kind of notation will become important when we start talking about logarithms. 5 is the base, okay? The base is the number that's being multiplied several times. The number 4, which you can see is kind of a superscript, or it's written above it, that's the exponent. And the term together, so 5 to the exponent 4, is called a power, okay? So that together is called a power. So let's look at a couple of examples. These examples, I'm going to express each of them as a power, okay? And you're going to see how things change in terms of what is the base in each instance. And I even have an instance here where we just have algebraic terms, W. So in the first case, okay, we have 7 times 7 times 7 times 7 times 7, okay, or 5 times. So that means all the numbers are the same, okay? So every number in here has to be the same in order for it to be the base. So the base here is 7. And if you just simply count them up, 1, 2, 3, 4, 5, the exponent is simply 5. Okay, it's a bad version of 5. In example B, it works the same way when you have an algebraic term, in this case W. So we have W times W times W times W, okay, so 4 times. So in this instance, it's all W. So the base is W. And again, if you count them, 1, 2, 3, and 4, the exponent is 4. Okay. In example C, we have negative 4 multiplied 4 times. And it's important to note that it's negative 4 in brackets. Okay. And every number here has the same negative sign. So it's the same number. So that means the base is actually negative 4. And I'm putting brackets around it because that emphasizes that that whole number, negative 4, is the base. And it's multiplied 4 times. Okay, so that means it's negative 4 to the exponent 4. In example D, you'll see that it's the same number, but it has decimals. And it doesn't matter if it's a whole number, like we had, okay, or a positive number, like we had in example A. Algebraic term, example B, a number with a negative in example C, or a decimal. Any of those instances can all be a base, okay? So in this case, we have 1.01, because it's used in all 4 instances. And we have it 1, 2, 3, 4 times. So it's 1.01 to the exponent 4. Example E just has the number 16, right? Not multiplied by anything. And if you have just a number, the reason I show this example is that means 16 to the exponent 1. Okay, so that means there's only one value of 16. So we often just write that as 16. But when you start multiplying and dividing exponents, knowing that the number 16 is actually 16 to the exponent 1 becomes important. Our last example, example F, you'll see that we have the number 4, but the first number here is negative. So they're not all the same number. And the reason I show that is because the base in this instance is not negative 4, okay, because there's a negative number there. But if you have a negative number, you can write that as negative 1 multiplied by the positive number, because negative 1 times 4 is the same as negative 4. So if we rewrote this as negative 1 times 4 and then times 4 times 4 times 4 times 4. Okay, you can see that we have 4 multiplied by itself 4 times, and we have a -1. So this notation is a little bit different than example C, because in example C, we had a -4 all 4 times. So in this case, we actually have a negative, okay, and then we have the number 4 to the exponent 4. And you'll notice I don't have it in brackets, okay, and that's because that negative is just multiplied on at the end. So this multiplies out to -4 times -4 4 times. This multiplies back out to what we started with, -1 times 4 4 times. Or, in the way it was written here, we had -4 times 4 times 4 times 4. Okay? So that's the clear distinction here, is that in this instance, example C, the base is actually -4. Okay? In this case, since they're not all negatives, the base here is just 4, not -4. Okay? So that's an important distinction when we look at doing operations with exponents. So, like I've noted in the previous example, we had an example with W, okay? And in this case, I want to show you it with algebra. Okay, so if we just have a letter, A, B, C, it doesn't matter. If you have a term A to the exponent n, that's equal to A times A times A n times, okay? So if you had A to the exponent 5, that's the same as A times A times A times A times A, okay? Or A to the n factors multiplied together, okay? And that still follows, like we showed in the previous example. If you had 2 to the exponent 5, instead of having them both as letters, that's 2 times 2, 5 times, okay? So it's important to remember, like we talked about, a power is actually the complete term, which is the base number or the base term to an exponent, to a number or a value in an exponent. And like you saw in our example E in the last slide, when you have just a number or just an algebraic term like x, if it's just that number, okay, it means 6 to the exponent 1 in this case. Or if you had just x, it means x to the exponent 1. It's the same as writing it that way. So from a notation perspective, we often ignore that and don't write it, okay? So I'm just going to give you some examples. This is just to reinforce the power, base, and exponent principle. So in this case, the first example just kind of lays down how to do it. The expression 7 to the exponent 5, the overall power is the combination of all those terms, so it's 7 to the exponent 5. The base is the number that's being multiplied, in this case 7. The exponent is 5 because it's raised to the exponent 5. For x cubed, the power is the complete term, x cubed. The base is x, okay, that's the number being multiplied, and the exponent is 3. For the next example, 4k cubed, the overall power is all of that, 4k cubed. The base is 4k, and the exponent is 3. In the next example, we have 4x squared. Okay, the power here is not 4x squared. You see how this is all in brackets? That means that entire term is raised to that exponent. If the brackets aren't there, then that's not the case. So for this example of 4x squared, the power is simply x squared. Okay, and then that is being multiplied by 4. If this was all in brackets, then the power would be 4x squared, but it's not. Okay, that's a very important distinction. So the power here is simply x squared. The base is then x, and the exponent is 2. The next example, we have -7 in brackets, again an important distinction, to the exponent 6. So the power here is the entire term, negative 7 to the exponent 6, because that's all in brackets. That means the base is negative 7 and the exponent is 6. The last example is the same as the one we just talked about, okay? We have negative 7 to the exponent 4, but it's not in brackets. So the power here is simply 7 to the exponent 4. This negative is just like having negative 1 multiplied by 7 to the exponent 4, okay? So the base here is 7 and the exponent is 4, okay? So this is a useful table for you to go back on to remember these types of distinctions, okay? And it may not seem that important right now, but when you place these numbers in your calculator, okay, it follows these rules, okay? It follows those rules. So if you don't do those rules properly, you're not going to get the right answer as an output, okay? So a few more examples here. Okay, so I've got 4 examples. 2 of them I've done for you, and 2 of them we're going to do ourselves. So A is 3 to the exponent 5. So you look here, it's 3 times 3, 5 times. Okay, pretty straightforward, pretty self-explanatory after what we've seen, which is 243. Example B, 5 to the exponent 3. Following that same pattern, that means it's 5 times 5 times 5, right? Because it's 5 to the exponent 3, or 3 times, which is 125. Next example, okay, negative 4, all in brackets, very key item to see here, to the exponent 3. So that's negative 4 times negative 4 times negative 4. And the answer is negative 64. And that's because negative 4 times negative 4, if a negative multiplied by a negative is a positive, that would be 16. Then you multiply that by the last negative 4. So positive 16 times negative 4 is negative 64. For the next example, negative 2, all in brackets again, to the exponent 6. That's negative 2 multiplied out 6 times. Okay, so I'm going to show you each one to show you how I get to the final answer, but then I'll kind of show you a trick to know automatically whether your answer will come out as positive or negative. So negative 2 times negative 2 is positive 4. Positive 4 times this negative 2 is negative 8. Negative 8 times negative 2 is positive 16. Positive 16 times negative 2 is negative 32. And negative 32 times negative 2 is positive 64. Okay, so this is positive 64. And the reason that this is the case, you're going to see, I'm going to talk about it in the next slide, is if you have a negative number in brackets and it's raised to an odd numbered exponent, 1, 3, 5, 7, 9, etc., your answer will always be negative. If it's raised to a positive exponent, so 2, 4, 6, 8, 10, keeps going, you'll get a positive number, okay? Sorry, an even numbered exponent. Okay, so again, this is the first special case. You saw this in examples C and D. If your exponent is an odd number, you get a negative number, okay? And if your exponent is an even number, you get a positive number. And that's only if it's a negative number all in brackets. In other words, your base is a negative number, okay? The second case that we've already talked about is when your base, okay, this number's not all in brackets, okay? It's not in brackets. So that means that your base here is actually A and not negative A. So if that's the case, when you have an exponent like that, let's look at 2 examples. If you have an exponent like that, it's the same as negative 1 multiplied by that term when you multiply it out. So looking at the 2 examples, we have negative 2, that's all in brackets, which means that's the base to the exponent 4. So you get negative 2 multiplied out 4 times. And remember, since this is an even number, that means you'll get a positive final answer of 16. But if you have negative 2 to the exponent 4, and it's not all in brackets, that's the same as negative 1 multiplied by 2 4 times, right? Because the base here is actually a positive number. So you end up with negative 16. So it's a small distinction, okay? And this actually happens on most of your calculators when you input numbers like this, okay? If it's a good scientific calculator, you have to do that distinction in order for the calculator to calculate it properly. So let's do some examples of this, okay? I want to reiterate this because it does become very important when you're showing your work on a test. So for each of these, we're going to write them out like we've been doing and then evaluate the final answer. So for A, we have negative 3, again, all in brackets to the exponent 4, which means negative 3 is the base. So we have negative 3 multiplied out 4 times. Okay, since the exponent 4 is an even number, I know the answer is going to be positive. Okay, but just to prove it, we'll go through each number. So negative 3 times negative 3 is positive 9. Positive 9 times negative 3 is negative 27. And negative 27 times negative 3 is positive 81. In example B, we have negative 3 to the exponent 4. But the negative is not part of the base, right? Because it's not in brackets. So we have to write that as negative 1 times 3 times 3 times 3 times 3. Okay? So remember the base is positive. So 3 times 3 times 3 times 3 will be 81. And then you multiply it by this negative 1. So we get negative 1 multiplied by 3 times 3 is 9. 9 times 3 is 27. 27 times 3 is 81. So we get negative 1 times 81, which is negative 81. Okay. Example C, okay, we have negative 4 squared. Again, negative 4 is within the brackets. So that's negative 4 times negative 4, which is positive 16. For example D, negative 4 squared, remember, the negative 4 is not all in brackets, so the base is actually a positive 4. So we have negative 1 times 4 times 4, which is negative 1 times 16, or negative 16. Okay? Example E, we have negative 1 all in brackets, okay, to the exponent 6. So if we write that out, we have negative 1 times negative 1 6 times. And we know it's a positive exponent, okay, or sorry, an even exponent. So because it's an even number 6, we'll get a positive answer of 1. I think you're starting to get the pattern. When we get to our last example, example F, we have negative 1 to the exponent 6. So that's negative 1 times 1 times 1 times 1, 6 times. Okay? Which gives us negative 1 instead of positive 1. Okay? So now I want to look at some more types of examples. This one being, what if your base is a fraction? Okay? And when your base is a fraction, it's the exact same. Nothing changes. Okay? So if you look at your example, 3 over 2 to the exponent 5, that's the same as 3 over 2 multiplied 5 times. Okay? Now, how I get from this first step to here goes back to the basics of fractions. Okay? So if you have two fractions, 1/2 multiplied by 1/2, when you're multiplying fractions, you multiply the numerators together and you multiply the denominators together. So this would be 1 times 1 over 2 times 2, or 1/4. And that makes sense, right? 1/2 multiplied by 1/2. So 1/2 of a half is a quarter. The same thing happens when you're multiplying all of these fractions together. So it's the same as taking all of the numerators, 3 times 3 times 3 times 3 times 3, divided by all of the denominators, 2 times 2, okay, 5 times. And if you multiply those out, 3 times 3 5 times is 243, and 2 times 2 5 times is 32. Okay, so all I'm using here are rules from multiplying and dividing multiplying fractions. Okay, dividing fractions would be a little bit different. So let's look at an example. We have negative 1 over 3 to the exponent 3, and again, keep in mind, negative 1 over 3 is all in brackets. Okay, so if we multiply that all out, it's negative 1 over 3 times negative 1 over 3 times negative 1 over 3, because the exponent here is 3. Now, when you see a negative number, like negative 1 over 3, the typical convention is to place the negative sign in the numerator. In other words, negative 1 divided by 3. Okay, but it doesn't matter. Either one of the numbers could be negative. I encourage you to just put it in the numerator. It's the easiest way to do it. So what this would work out to is negative 1 times negative 1 times negative 1 divided by 3 times 3 times 3. Okay? Because you're multiplying fractions together. So you multiply all the numerators, or the items on the top of the fraction, and then you multiply all of the items in the denominator, or the bottom of the fraction. And if you do that, you get negative 1 divided by 27. Now, like I said, convention is to place the negative on the number in the numerator. But if you put it on the number in the denominator, the answer doesn't change. Okay? If you did that, you'd have 1 times 1 times 1 divided by negative 3 times negative 3 times negative 3, which would give you 1 divided by negative 27. But these are the same numbers. Okay? Put those both in your calculator, you get the same number. It doesn't matter where it is. Okay? The final convention that you see a lot of people do after it's multiplied is to have just a negative before the whole fraction, and you have 1 divided by 27. Okay? Any one of those still yield the exact same solution. Okay? So just to kind of further that, let's look at 2 more examples. First is 3 over 5 to the exponent 4. So again, multiplying it out, the base is 3 divided by 5, and the exponent is 4. So that means it's 4 times. Okay? And if you follow the same convention for multiplying fractions, you get on the numerator 3 times 3, 4 times, divided by 5 multiplied 4 times. And what you get there is 3 times 3 is 9, times 3 is 27, times 3 is 81. And in the denominator, if you multiply this out, 5 times 5 is 25, times 5 is 125, times 5 is 625. Okay, so I did that by doing kind of the basic math. The next example, you'll see we get to larger numbers. And I mean, on both these, you could just put them in your calculator. It's more than fine. But for some of the basic ones, sometimes it's quicker just to do it in your head. For B, you have negative 2 over 7 to the exponent 5. Okay, so negative 2 over 7 is all in brackets here. Okay, put that there by accident. So if you write that out, you get negative 2 over 7 multiplied 5 times. Okay, so just like in the previous example, okay, I've left the negative in the numerator just because it's the convention that I'm used to. So if you multiply this out, you get negative 2 in the numerator 5 times, because that is the exponent, remember, divided by 7 5 times. Okay, and if you multiply these out, you get on the top, you get negative 32, divided by 7 multiplied out 5 times is 16,807. Again, When you get to those ones, I don't necessarily think it's faster for most of you to do that in your head, so you could obviously use a calculator for it. Okay. So now that I've talked about exponents, I want to talk about what happens when you multiply them, two items with exponents together, divide, or when you have a power, okay, so in this case, a to the exponent n, and that's raised to another exponent, okay? And there's three simple rules to apply. The first one is if you're multiplying them together, okay? And keep in mind for each one of these rules, especially for multiplication and division, when you're multiplying two powers together, they have to have the same base, okay? They have to have the same base. If they don't, so if you have 2 to the exponent 5 times 3 to the exponent 5, these rules do not apply because the base, in this case, which is 2 in one and 3 in the other, is not the same, okay? If the base is the same, let's say it's 2 to the exponent 5 times 2 to the exponent 2, the rule is very simple, okay? You add the exponents together. So that's the same as 2 to the exponent 5 plus 2, or 2 to the exponent 7. Division is the opposite, okay? So if we take that same example that we just did, and we have 2 to the exponent 5 divided by 2 to the exponent 2, instead of adding, you simply subtract the exponents. Again, it has to be the same base. So in this case, it's 2 to the exponent 5 minus 2. Okay, it's always the exponent in the numerator minus the exponent in the denominator. Okay, it's never the other way around. So if you do this, you get 2 to the exponent 3. I'm going to give you an example that shows kind of how this works again in a later slide. Our last one is if you have a power, okay, so let's say 2 squared, and that is all in brackets, including the exponent, and it's raised, let's say, to the exponent 3, okay? So if you have that instance, then you multiply the two exponents together. In other words, this becomes 2 to the exponent 2 times 3, because you're multiplying the two together, which is 2 to the exponent 6. Okay? So those are the three major rules when it comes to operations with powers. Okay, so let's look at a few examples. Okay, so let's look at a couple examples. Use the laws of exponents, and we're going to evaluate each of the following. Example A, 3 to the exponent 5 times 3 to the exponent 2. So first thing to notice is they have the same base, so you can multiply them together using the rules of exponents. So for A, 3 to the exponent 5 times 3 to the exponent 2. Remember, when they're multiplied together, it's the same as adding the exponents. So that's 3 to the exponent 5 plus 2, which is 3 to the exponent 7. Example B, 2 to the exponent 8 divided by 2 to the exponent 5. So 2 to the exponent 8 divided by 2 to the exponent 5. So they're the same base. Again, they're both 2. And when you're dividing, you can subtract the exponents. I like writing them in fraction form. It's easier to see which one I'm subtracting from the other. So that's the same as 2 to the exponent 8 minus 5, which is 2 to the exponent 3. Item C, okay, 3 to the exponent 2, and that's all in brackets raised to the exponent 5. So when you have something, when you have a power raised to another exponent, okay, 3 to the exponent 2 to the exponent 5, that's the same as multiplying those exponents together. So we have 3 to the exponent 2 times 5, which is 3 to the exponent 10. Okay. Looking at a few more examples. Okay. Let's start with example A. We have negative 4 to the exponent 3 times negative 4 to the exponent 7 times negative 4 to the exponent 5. So they all have the same base, and it doesn't matter if you're multiplying together 2 or 3 or 4 of them. Okay, you can still add the exponents together. So this is the same as negative 4 to the exponent. Okay, so let's look at a couple more instances where maybe the exponents are different scenarios. first example I'm going to look at is when your exponent is 0. So let's say we have 3 to the exponent 5 divided by 3 to the exponent 5. Well, remember, you would subtract the exponents. So that would be 3 to the exponent 5 minus 5, or 3 to the exponent 0. Okay? If we write this again in fraction form, the way you saw me do it in the past, you'd have 3 to the exponent 5 divided by 3 to the exponent 5. Now, instead of using exponent rules, if you just multiplied those out, you'd have the same number in the numerator and the denominator, 243 and 243. And any number divided by itself is equal to 1. So what that means is any number that you have, okay, or we can call it algebraic term, anything to the exponent 0 is equal to 1. The only case of that is if you have the number 0 to the exponent 0, okay? That number is undefined. But in every other instance, 3 to the exponent 0, 155 to the exponent 0, it doesn't matter, it's equal to 1, okay? So, in all of these instances, let's go through these examples. Example A, 8 to the exponent 0, okay, 1. B, negative 4, all in brackets, to the exponent 0, again, is 1, okay, because you have just a power, okay. 2 over 3 to the exponent 0 is 1. Example D, negative 5 to the exponent 0. Okay, remember, the negative's not in brackets. So this is the same as negative 1 times 5 to the exponent 0. And 5 to the exponent 0, okay, any number to the exponent 0 is 1. So you're left with negative 1 times 1, which gives you negative 1, okay, not positive 1. In all of these other examples here, okay, it was just a power, okay, so a base and an exponent. In this case, we have a negative 1, and then we have the power, okay, which is 5 to the exponent 0. An important distinction to make, okay? Our last example, example E, we don't have anything, we just have a power, 2.03 to the exponent 0, so that is equal to 1, okay? So our last topic to talk about, okay, I know we've talked about a lot of types of exponents, is if you have a negative exponent, okay? So looking at an example to explain to you what a negative exponent is, if you have 4 to the exponent 3 divided by 4 to the exponent 5, okay? Because they have the same base, you can subtract exponents, okay? So that would be 4 to the exponent 3 minus 5, I wrote 3, which is equal to 4 to the exponent negative 2, right? But what that means is if you write it as a fraction, if we wrote it in its pure form, 4 to the exponent 3 divided by 4 to the exponent 5, and we wrote it like we did at the start of this lesson, where we wrote all the 4's out, okay? If you have a 4 in a numerator and a 4 in a denominator, okay, the same number, that's just 1, right? So we can cancel the 4's in both. And what we're left with is 1 divided by, if you take this one step further, 1 divided by 4 times 4, which is 1 divided by 4 squared. So what you'll see is 4 to the exponent negative 2 and 1 divided by 4 to the exponent positive 2 are the same number, okay? So what that means is if you have anything to a negative exponent, that's the same as 1 divided by that same power, but to a positive exponent. So if you have 2 to the exponent negative 2, that's the same as 1 divided by the same power here, but to the positive exponent, so 2 to the exponent 2, okay? That works with both numbers, okay, as well as algebraic terms. If you have x to the exponent negative 2, that's the same as 1 divided by x squared, okay? So let's look at some last examples for this lesson. So let's show you two examples. Simplify 2 to the exponent negative 3, and then negative 3 all in brackets the exponent -2. So using that rule, we can write 2 to the exponent -3 as 1 divided by 2 to the exponent +3. Again, all we're doing is changing the sign of the exponent from negative to positive, which is the same as 1 divided by 8, because 2 times 2 times 2 is 8. In example B, -3 to the exponent -2. Again, remember the -3 is all in brackets, so that's actually the base. So you can write that as 1 divided by -3 to the exponent +2. Again, you're just changing the sign of the exponent. And -3 squared is the same as 1 divided by -3 times -3. And the negative times a negative is a positive. So -3 times -3 is +9. So we get 1 divided by 9. Okay? So that was all I had for this first lesson on exponents. Please try these practice problems. There's a lot of rules of exponents, but they do come in handy, especially when you start talking about exponents when you have algebraic terms, so x and y and other numbers like that. Okay, so if you have any questions, just send me an email. Thanks, everybody.